Okay, so I already made one video on this that it's just far too long. So I'm going to try to shut this down and make it a lot shorter to describe why uh, mechanical advantage and the idea of mechanical advantage, for instance, in a 3-to-1 ratio broadhead, as purported by many, is simply incorrect. So let's look at this idea of a ramp. This is what people base the idea of mechanical advantage in a broadhead on. And so if we imagine we have a ramp and we're trying to move a weight from something heavy like a box, as an example, from the bottom of the ramp, and we move that up to the top of the ramp. So we push it up here. And we do so by exerting a force on the box and sliding it up the ramp. So it turns out that the work done here is going to be equal to the force times the displacement, which we'll call d. And it's important to understand that this is not just a length. It happens to be that the displacement here is the length of the ramp, but it's not just the fact that the ramp is this long that means the work is F times L. The work is how much force were you exerting on this box as you pushed it through this amount of displacement. The box had to move from here to here. Okay, it moved up the face of the ramp. And it is true that if you compare the force required to move this box up the ramp of certain height h, that as the length of the ramp gets longer versus the height, then the force decreases. So it requires less force to push the box up the ramp of height h. The shallower this ramp is, the longer this is. And so the mechanical advantage is defined here in this case for a ramp as the length divided by the height. Okay, so this is the standard idea. And applied to a broadhead, the argument goes that, well, a really long broadhead like this, we can think of it for a two blade as being two ramps, one in either direction. And so we would take the length divided by half the width of the broadhead, and that will give us our mechanical advantage. That will tell us how much easier this is to push through an animal. And then the idea is, well, there are two of these, so you have to divide that by two. So that ends up giving us our 3-to-1 ratio. And so something that's a 3-to-1 broadhead versus a shorter, stubbier broadhead like this one, you would say would have much less force acting on it as it pushes through an animal, and this one would have much greater force. And it turns out that that's simply not true. And the reason is because this is misapplied to the case of a broadhead. If we look at this, notice what's happening is we are taking material from the bottom of the ramp and displacing it to the top of the ramp. But if we imagine these broadheads penetrating animal tissue, let's say that this little spot here is the place where it hits the animal, the tissue that's here doesn't get displaced to here. That's not what happens. And the same thing is true here. If we have some tissue here, it doesn't get pushed out and then pushed up this way. This displacement is not the displacement of the tissue. What happens is the broadhead cuts and the tissue actually runs right along this back here, at least in the case of a two blade. Same thing here, the tissue just runs straight along this. So the displacement, the force times the displacement for a broadhead is not along the cutting edge of the broadhead. It's along the thickness of the broadhead. In other words, this is looking at these broadheads from the side. This is meant to look like an iron will. This would be something more like a tough head, both broadheads that I like and have personally. If you imagine the material hitting here, the broadhead impacting the animal here, the displacement is just up and then back this way. Okay, at least initially the displacement is just along the thickness of the blade. Okay, so we get some displacement this way or some displacement this way. And we see that in both of these cases, the mechanical advantage really is basically just the angle of the head, how steep this angle is here. The steeper this angle, the better the mechanical advantage. But in either case, you don't really have to worry about it because the displacement is just the thickness of the blade. And so both of these blades have incredibly high mechanical advantage, and it has nothing to do with the profile of the blade because nothing is displaced along the edge of the blade it's displaced along the faces or the side of the blade. Okay, now when we get back to the ferrule, again we have these longer ramps, and again the sort of width to the length of the ramp here is quite long, and there's good mechanical advantage here. So yes, mechanical advantage is important in a broadhead. It does not have anything to do with the thickness, with the profile or the width of the broadhead. There is no work done displacing material along the edge. The displacement happens along the thickness of the broadhead, and therefore mechanical advantage just does not play a role, at least not this kind of mechanical advantage in the force. This is bore out. I believe that Bill from Iron Will has talked about his push force testing. I think Cody Greenwood has also done some of this at the Trad Lab, where the difference in push force to push this 3-to-1 broadhead through versus this much less than 3-to-1 broadhead through is actually really not that much difference. Now, where this could play a role is with something more like a chisel tip. In a chisel tip, you don't have this nice thin blade that initiates the penetration of the animal. Instead, you have this big thick chisel, and then after that, you might have some blades after that. So in that particular case, this is not this is sort of conical, or it's got almost like a pyramid of shape here. The longer that chisel tip is, the better the mechanical advantage, and the less force it's going to require to push this through soft tissue. The shorter or stubbier that chisel tip is, the worse this is going to be. So it's not that mechanical advantage plays no role in broadhead. It's just not the role that many have propagated as being important. So the question may be then, why do some tests seem to show better penetration for long broadheads versus short broadheads? And I think the answer to that's relatively easy. If both of these make essentially the same width cut, let's say that in both cases the cut here is about an inch wide, then the 3-to-1 broadhead just uses a lot more edge to make the same cut. So, for instance, if we have a cut that is basically an inch wide like this, the 3-to-1 broadhead has 6 inches of cut, making this 1 inch wide cut. So 6 inches of blade length, making this 1 inch wide cut, where this one has much less. And so just the doling or the damage, the edge damage, is going to be spread out over a much longer length for this long broadhead than it is over this short broadhead. So you have two options. You build your long broadhead from a cheaper steel where you might have more edge degradation, but you've got a lot more edge to work with. So the edge degradation sort of gets minimized from the fact that there's just a lot of edge for the same length cut. On the other hand, you could use a shorter broadhead, but you're going to want a better steel. A steel that doesn't chip, a steel that has good edge retention. And in that case, it doesn't really matter that we have less blade surface making, or less blade edge making the same cut, because it's a much higher quality steel, and it can handle that cut much better. And this is a better explanation for what's going on with mechanical advantage than the one purported by many in the heavy aero community.